Welcome back, everyone, and we're back with another video. And again, we're going to continue more IK work. The last two videos we did an IK solver I'm calling AIM, and then in the last video we did generating T-poses. Now we're going to go back to working on our new limb solver. So it's another IK solver, and it's meant for just two bones. I've done this many months ago, like a simple one, but they only worked on like these bones that they weren't like attached to any meshes. Now that we're dealing with real meshes and we were trying to really control where the elbow goes and where the knee goes, the IK solvers had to be rewritten and everything else. And so we're back to the limb solver, but this one works on real meshes, and we're going to really start moving characters around, and it's really going to be a big part of the next two videos after this. We're going to do an IK dance. But we need the limb solvers, the AIM solvers, and everything, and the T-poses to work perfectly together. So today we're going to do the limb solver, the brand new one, and we're going to, a lot of the same ideas, but just the code has changed a bit, and we're going to have fun with it. And I'll have a little surprise at the end for future videos after we're done with IK. So we're going to start off with Vegeta again. No surprise, he's going to be our demo model for many moons. So we're going to start off with simple setup page that we normally have, loading up Vegeta, and to make things easier, I'm going to only load up I think it's just 4, just the skeleton. So let's just deal with the skeleton for now, and then we'll play with the mesh afterwards, because it's easier to see everything without the mesh in the way. So, all right, so we got our skeleton. We don't want to see Vegeta yet, but we're going to deal with his bones. So we're going to start doing the limb IK solver, and we're just going to work on one arm for now. So let's see. So for the first thing we're going to do, we always have to kind of set up an IK chain. It just makes things easier when you have like an array of bones that we're working with. So this is going to be just a two element array, which is bone A and bone B. You kind of your upper arm and your lower arm. And we're going to define an end position. Basically, it's called the end effector, where we're trying to reach to. So we defined where it is. That's where it is in 3D space. And we're going to have to keep track of world space parent and world space child, because like if you're new to the IK solvers, you haven't seen a lot of my other videos, it's kind of important because you need to know where your parent is to be able to save your rotation for your child. You'll see that again and again a lot, but we always need to keep track of what the bone that we're currently working on, what's our world space transform, and we need to know its parent, because knowing its parent allows us to convert world space back to local space. So that's the big important reason why we need to keep track of both. So the first thing we're going to do is we're going to get the parent transform. I have a false because if I set it for true, it gets the entire world space from the bone that I selected all the way up. If I say false, it means I only want the parent and up, or lower, wherever. Yeah, basically up the tree. And then once that's done, so that means so right now, like I'm starting with the IK chain. So the IK chain is usually just these two bones, and I'm saying, well, I want this world space. So the world space goes from here and works its way down, and it calculates the world space that way. And then from there, I take the bind of the chain, the bind pose, and just add it to the world space. So this way I create my world space child bone. So the world space C is this bone right here. It's the upper arm. And right here I have something called a line chain. This is from our previous video where we generate T-poses. So the idea is that I'm actually kind of just, like, ideally you wouldn't do it this way. You would actually align all your bones and then you do all your IK stuff. But I'm putting everything here in one big, call. So this way you kind of see all the steps that you would generally take if you want to do the IK perfectly. And that gives me a chance to kind of uncomment this line, and you can see how the result is if we don't have a T-pose. So like I said, it's more for learning purposes. You would definitely just want to align your T-pose before you even deal with any IK stuff. So that's what I'm doing there. I'm applying the T-pose just on that one chain alone. And I'll show the code later. It's the same from last video. It's just more streamlined. I fixed it up a little bit since the last video. And listen, so we got our world transforms. So the first step is we need to define an IK target. So the IK target is basically the start of our first bone in our chain and some type of end effector, which I can't display yet. And then from there we define the direction from the shoulder to the end effector. We determine what the up direction is and what the left direction is. And if you remember, the aim IK solver is that we have to define an up direction. So our forward direction is going to be from the shoulder to the end effector, and then we define an up direction. And that up direction is going to be where the elbow points. So ideally, I want the elbow to point this way, kind of like where the red dot is. That's really like the left. Because red is X, green is Z, and the gray goes up to Y. That's the Y-axis. So essentially, IK target generates the end effector, the length to get to the end effector, and the 3 axes that defines the whole rotation that we need to do. Because it's important for the aim solver to have all that information. So if you're just coming in now, check out 2 videos ago to the aim solver, because this is kind of an extension of that video. And then once we have our IK target, we do our aim solver. But the only difference between this, this is what our aim solver kind of looks like now. It calls aim bone and then does the world to local transformation. The idea is that aim bone, the aim solver, the bulk of it is going to be used in a lot of solvers. It's like the starting point, because it allows us to aim toward it and aim like the bending direction, where the elbow is, where the knee is. Because when we do an IK solver, we want to have a bend. So we need to know what direction that bend is, and it's kind of like a triangle, and I'll show it to you in a little bit. So this is our aim solver now. It does everything that the aim solver does except transform everything back to local space. It keeps everything in world space, and it shoots it right back out as world space. So that makes life really easy. So this way I can reuse the function in a lot of places, and then just do the transformation at the end. So now if I uncomment the IK target, refresh. So there is the red line, the red dot, that's our end effector. That's where we want to go to. So the black dot is our shoulder, that's the starting point, and the green line is the forward direction. That's where we want to go. The blue line is that up direction. So if the arm is going this way, the elbow is going to go in that direction. And that X line actually becomes our rotation axis. So we're going to be using that axis for rotation. Right? But the first things first, we need to align everything. So since I did the aim bone, it returns back the bone quintorian rotation, and all I'm doing here is converting it back to local space and then saving it right back into that bone. So once I did that, refresh. Now the arm is pointing toward the end effector, and that's what we want. We want the starting point to be that rotation. So now, see, as you can see, the elbow is here, and it's pointing in the right direction. So if you want to have a better look at it, we can bring Vegeta back, refresh, and there you go. There's his arm. He's pointing exactly where we want it, and his elbow is right around here, and it's pointing in the direction that we need. So again, like I said, we're reusing our aim solver. So okay, so now we have it. So now the arm is aligned perfectly. So it's aligned, it's perfect. Now what we have to do is now treat this as triangle trigonometry. And what we're going to use is, this is like the most important piece, is the law of cosines, the SSS equation. I don't know why it's called SSS, but it's just the triple SSS. So oops. So let's look at this right now. So a triangle has three sides. So one side is from the blue dot, for the black dot to the red dot. So that's our long side. Oh my god, I got it. So that we can call our C side of the triangle, right? And not switching tabs. But right now it looks like a flat triangle, but because we haven't done any of the rotations yet. So from black to red, that's going to be C. The first bone is going to be B, or actually be A, and the second bone will be B. Oh my god, sorry. So like I said, this is the direction toward the end effector, and this is our first bone, and this is our second bone. So the one important thing, I'm not doing this again. The one thing why we're using that specific equation is because number A, we have no clue what any of the angles are. Absolutely none. The only information that we do have is the length of every single side. So we have three sides, and we know the length of each one of them. So by just having that much information, using this equation, we can actually solve the angle of every side very easily. And I'm doing that again. So if that's A, let's say that's the upper arm, that's the lower arm, and that's our end effector. So the first thing we want to do is be able to bend this bone, the first bone, which will be angle A. So to do angle A, you just basically do something with B and C, and then A will be the extra, like the outsider, and just like the equation is down here. You have, let's look at like the answer for C, which is A plus B minus C. So if you're trying to find C, the angle C, that means the length is the opposite. So that means you have to use B and A. But like I said, since we want this angle A, that means the sides we need to work with to add together is the length to the end effector and the length of the bone subtracted by the length of the second bone. So all the equations are all the same. Like I actually use just one function and just swap out the lengths, because it's basically you add two lengths together and basically subtract the other. And then the other is the opposite of the angle that you're looking for. So, the subtracting B gives you angle of B. The subtracting of C gives you angle C. Now, I say subtract. Yes, I say subtract, but then you also have to exclude it from the division, from the denominator. So basically, A plus B minus C, all of them squared. Well, you have to square them first before you add them up, but and then it's 2 times A and B. So it's the two bones, and it's like it's rinse and repeat. It's very easy. So you can just write this one function and just pass in the exact idea that you want. It's like if you want the angle, just exclude or treat C as the length, the opposite of the angle. So there we go. So we don't need this because this is the end of that. So like I said, step 2 is we need to rotate the first bone. And like I said, we know all the sides. So we have the sides. So A length is the first bone, B length is the second bone, and length C is the distance to the end effector. And then we have the law of cosines SSS. And this is what the equation looks like. Excuse me. And like I said, I basically copied exactly what's on this page. That's where I got the equation from. So by using this one function, we can solve every angle of the triangle. We just got to choose A and B and know what C is. And C is the opposite of the angle we're looking for. All right. So like I said, so I'm looking for the angle between A and C. So B is the opposite. So that's why it's in the third position. Even though like the equation's A, B, C, A and C is really the sides of the angle. The angle that actually creates the angle that we're looking for. So this one gives us a rotation, and so that's a rotation, and then we take the axis of the target. And like remember, I said that this red line, the x-axis of the target, is what will be used for rotation. So the gist of it is that I rotate the entire arm and have it aimed perfectly toward the end effector. Now that's perfectly aligned. So basically, I'm taking this 3D object and essentially making it 2D. So now I can actually rotate it in theory just like a 2D object, because I have the axis, which is x, which you can't see, because now, like say, we're 2D. So now I just need to move it from green to blue. I just need to rotate it by that specific angle. And like I said, I use that axis for rotation, and I take the negative direction, because rotation in, I don't know if it's my engine or just GL in general, it goes in the opposite direction. So even though the angle is whatever it is, do the negative, and it rotates just right. So I have that translation rotation. I'm gonna pre-multiply it by our bone, the one that we got the results from. So everything's in world space right now. So this BQ currently is the world space rotation of the bone after we did the aim solver. So now that I aimed it, now I'm going to rotate it away from the end effector line. And I want to make a copy of it, because now that's our world space. Because for the next bone, I need the world space as well. So this way, instead of recalculating the world space for the next bone, just make a copy of it. So this way I can use it, so I can say, so you don't process the entire chain all over again. And then we do the local space conversion. We take the parent, we invert it. I'm just saving it, so this I'm not recreating more and more variables, because JavaScript, the more variables you create, the less efficient it is, especially since it's a float 32 array for each one of these that I generate. And pre-multiply and update to the bone. And if I click save, it will now rotate. And now that is the exact angle I need to be for the triangle. So there you go. We saw, and now the idea is rinse and repeat. Now we take the other side. So we got B and C. Now we need to get the angle of A. Now we need to get the angle of C. So for angle of C, C is the opposite. So we say A plus B minus C. And like I said, now it's like the first equation. So we update that. So that means the first bone is done. We're done and updated, all and good and jandy. It's all good. Now this one's a little trickier, even though it's the same thing. So like I said, we know we want the two bones, and the length effector length is the opposite. So it's straight through A, B, and C. And we take the bind pose of the rotation, because I don't know if I mentioned in the video, is that when I apply the T pose, I'm not actually modifying the bind pose for the actual armature. I'm actually modifying the bind pose for the chain, because when I generate a chain, I make a copy of the bind pose. So this way I can leave the armature unaffected, but still have a copy of a different bind pose for that specific chain of bones. So this way it's the straightened version, the like nice and straight, to make everything, because once everything is nice and straight, it's really easy to do the rotation, or to calculate the rotation. So since we know what the straight rotation, perfect rotation is for that bone, we just take that rotation from the T pose, and we multiply it by our world rotation. Oh no, sorry. So so we take the bind pose and we multiply it by our world position from bone 1, the first bone, because remember we made a copy. So now we know so essentially from here we're generating the world space location of the second bone, and then we add in the rotation, and then we invert it and we update it. Done and easy. Now the only tricky thing here is this. Let me take this part out. Now, when this generates it, it does generate the correct angle in theory for that specific triangle. Refresh. All right, and it's not perfect. Like it looks off. You're like, wait, what the hell's going on? But if I say pi minus, now it's pretty much on the money. The reason why is that the way the rotations works here. So even though the angle I got was correct for here to here, we're applying the rotation. Trying to see how can I describe it. The idea is that the rotation, the way with GL is, or the way it's done, we're kind of going from from right to left. The notion that you're rotating this way. Zero is here, and then like pi is this way. The thing is up backwards. So instead of like rotating like from this angle from A to B, we'd need to rotate from B to A. So it's the opposite. So if I'm going 40 degrees from B to A, I need this angle to be the inverted version of it. So I got to take 180 degrees minus 40, which gives me 140, and that actually gives me the exact rotation from left to right. Like I said, it's a little tricky. Like this actually screwed me up a lot. Then this example doesn't really show it very well. Let's see if I do it again. But just keep that in mind. Like sometimes even though the angles are correct, the direction in which you're rotating is not correct. So that's like the one little thing I learned. So yeah, I can't think of it. Like what I was working on like a few weeks ago, that really I noticed it. But this one, it's like the idea is that I'm rotating from red to black, but I can't rotate from red to black. I need to rotate from black to red. So that's why it's reversed. You got to get, like I said, this is a straight line, right? So it's a straight line. So that, like I said, you're curving around from red to B, from red to black. So like I said, just do the reverse and you're good. It's hard. I can't explain it because I wish I remembered how the arm was currently when I was working on it, because that actually screwed me up for a day or two. And then I kept moving the end effector, and eventually saw an end effector, and I noticed that the angle. It's like, wait a minute, if I go the opposite direction, I was like, oh. So I made sure to write myself a note, but that's the reason why. So even though the angle is off, it is correct. Ideally, it's not where you're rotating from. So that's why you do pi minus, because you're going from like left to right, from right to left. So when I want to go 70, to go the opposite. So there you go. And that's it. Yeah, that's it. And it's like I said, it's right on the money. Done. It hit the target. Now, if I take away the T-pose, and that means that the chain now only has the original bind pose for the two bones. Empty. Now you can see that it's a little off. It's not perfect. It's close. It's very close. But that's because of the see how this isn't perfectly straight. That little angle, that is what's causing that to be misfired. So the more misaligned those two bones are, the more misaligned your end effector is going to be. So that's why I said if we generate a T-pose, make everything perfectly straight, then it's very easy kind of just to move the lines exactly where we need it to. And like I said, by using the aim solver, we kind of convert everything into like a 2D type of thing. So everything's a nice straight line. Now we just got to move the two lines exactly where they need to be. This needs to be at that certain angle, and that needs to be a certain angle. Yeah, and that's it. And we got the IK solver limb. And let's see, bring Vegeta back. Refresh. There you go. And the arm is exactly like the elbow is exactly where we need it to be. See, perfectly rotation. Like I said, as long as we keep everything aligned just right, it's very simple. Like it's just simple trigonometry. And the aim solver is really what helps us bring this 3D thing into kind of a 2D space. So it's a lot easier. Like I said, everything is aligned, everything's straight. Then it's very easy just to bend them on a specific axis. And like I said, since we know where the forward direction and where the elbow is, that final like axis that we define by using a cross product is our rotation. So this we can just rotate things. All you have to do is make sure you're going in the right direction. That's it. So I think for the first bone I just got it with a negative radians, and for the second bone I just had to subtract from math.py. And I've tested this on 3 different meshes with 3 different bones, and this IK solver works. So we're good. So there you go. We're good for that. And yeah. And so like I say, this is the long version. And then we have the right arm, which I simplified everything down. So we have align chain, do IK. And do IK is, it's all the main steps. We do, the world transform, we create the child, we create our target. This creates a debug. This is not needed. We check the distance between the distance of the target and the distance of the chain, because if the target is actually far away, like think about it. Our arm is my arm is like maybe 2 feet. Not really, but let's just call it 2 feet. And if the target's 2.5 feet, there's no bending. It's just a straight line from there. So at that point, we just use the aim solver. Just straighten it out. Just that's it. And then if the length is less than the distance from shoulder to the end effector is less than the total length of my arm, that means I need to bend it to reach it. And that's the only extra step we're adding to this. That's it. Because if you actually tried to do the math equations when there's no angles, everything gets screwy. Like actually the arm doesn't even show up. Like it just disappears. Like you get like a not a number or infinity, or you get these weird values. So you got to make sure that the length to the end effector has to be less than the length of your chain. And like I said, you have the length of every bone. So just add up. So when you're creating your IK chain, you just add up the length of every bone, and that gives you your total length of your bone, of your chain. And that's do IK. And you have our aim bone. You have our online chain. It basically does the aim without the without aiming the elbow. So it's this. So if you remember the T pose value video from before, like I said, it's just more streamed down to a simple small function. I had tons of comments here, so anyone can understand what's going on. And then we have our old limb solver, our new limb solver that uses the aim bone. And this is the one we just went through, but now this is a more streamlined version. It uses aim bone and, nice and smooth. So it basically is like 3 functions. You kind of have your do IK that kind of sets up our targeting and everything else, and then chooses which solver to use, and then you have our solvers and everything else. So we can do the end effector for the right arm. In this one, I actually chose a different. Yeah, I chose a. No, that's not right. Oh yeah, I created a new function for vect called from polar. So this way, I can create angles very easily by using polar coordinates. So this way, I'm defining that blue line. I want the elbow to be pointing in that direction. So now the elbow points in that direction. That's my end effector, and everything aligns perfectly. And yeah, could do the same thing with left leg and right leg. Ta-da! I was thinking about figuring if I could do an IK for Final Flash, because his leg is already kind of in that position anyway. But it was like, I don't feel like sitting there figuring out the end effectors and where the elbow needs to go. But yeah, like I said, you can very easily, like if you know if you can define the end effector and just define the direction where you want your elbow to be, then you can make these poses very easily. And the reason why I'm trying to do it this way is because I want to try to do the Ubisoft IK rig example. So this way we just define directions. So we just define a direction toward an end effector and the direction of an elbow. And then we can apply an entire chain to it. So if this is a 2-bone chain, what happens if I was using like an octopus arm that has maybe several bones? The data is the same. It's direction and bend direction. So by using a different solver, like I think I had one I made a couple of months ago called like circle arc, you can make a circle arc based on the exact same data. So this way I can have, like I said, save the exact same data and actually apply it to different types of bones and still get the same results. You should definitely check out some of my old IK solvers if you're new to this, because they're great, because I created a bunch of ones like half a year ago. Like now I'm kind of going back and refining them and make sure they will work with 3D meshes, because I discovered that the ones I did work, even though they look like they work, the rotations don't take twisting into account. And this time I'm taking twisting into account, which the AIM solver, the new solver for they created just recently, solves that problem. It allows me to create a direction of where the bend is going to be. Like I said, to try to convert everything into kind of like a 2D space to make things easier to rotate. And there you go. There's Vegeta all bent up in IK. And the next 2 videos, we're going to do the IK dance. So now that we can aim everything, we can do a T pose. So that means we can do our IK stuff like perfect. Next thing we're gonna do is start applying random noise to our IK stuff. So this way we can and just actually move the end effectors, and by doing some randomness and a bunch of other things, I actually finished writing it's gonna be a 2-parter, and I already finished writing all the new code for it, and it's ready to go. I just need to package it up and record the video. So hopefully soon we'll do the IK dance. So that's going to be fun. We have Vegeta dance, just randomly dance based on applying noise to rotation. And basically we're going to do noise with IK. Like I said, all you got to do is move these points around with predefined constraints, and then we're done. And you just got to apply it in different, like the feet does something different, but whatever. It's going to be fun. It's totally awesome. I'm like totally excited. I can't wait to get those videos recorded. And also want to say, once we're done with the IK dance, we're going to go to spring physics. And the other day I found an awesome mesh that it would be perfect for spring physics, because it's basically a gyroscope, but it's not a normal gyroscope. If anyone is ever played Fortnite, this is called the Baller. This is a vehicle that you can drive that you can drive around. And I found a mesh. I'll eventually show a link to it when I actually do the videos. And I don't know if you can tell, but the ball does rotate. There's several, like maybe like 5 or 10 videos ago, I did a video about how to do arc length to actually control the rotation of spheres. So I kind of went back, refixed up the code a little bit, and applied it to the sphere component of this thing. So now I can actually perfectly control the ball. So the idea is that there's going to be like 2 or 3 parts for the spring physics, and the first part is going to be about spring movement. So with the ball, hopefully will roll. And then when you tell it to stop, it kind of just springs back and forth a little bit. Kind of like that until it stops. Because it's a ball. It's not going to stop perfectly. It's not going to stop on a dime. So I thought that would be an awesome piece to have. This would be an awesome piece. And then the second video of spring physics will be dealing with spring physics on rotation instead of on position. So instead of translation, it's rotation. And and the inside part of this ball, I was gonna have it like rotate back when you're moving forward and rotate forward. It's going to move based on how you're moving, and then when the ball stops, the inside will actually spring itself back into position. So this way you'll have a spring rotation using the inside gyro, and then the position rotation, position spring, controlling the movement of the ball itself, and yeah, so this way you can, so by using those two spring components, one for movement and one for rotation, we can actually bring life to this ball and movement. And we can, and like I said, the spring physics that I was been playing with a couple weeks ago, you can go really fast, and then when you stop, it kind of just slows down and then springs to a stop. And you can configure. There's two equations that I fixed up. One gives you a good like springy, and one's kind of like an eased springing, which is pretty neat. And the change of direction is really cool, because if you go forward and then you want to go back really quick, it actually slows down and then moves. So it's really some of the it's really cool spring equations I managed to find and implement for some testing. So we're gonna implement that with this ball, and once we're done with spring physics, I wanted to go back to more animation, but I was thinking, since this ball is really cool, maybe we'll go experiment with WebXR, because we've done WebVR like over a year ago, and the API has been revamped and it's completely different now, and now it's called WebXR. So I think I'll revisit WebVR, or like virtual reality in the web browser, and actually put ourselves in the ball. How awesome would that be to be in the ball using a web page, and then maybe add controls to the, because I can actually control a lot of things in this ball. Those hand controllers I can actually control them. The feet things, the cannon, or this gun can actually rotate around and left and right. It's just great setup. This is ideally this has been ripped from the game, so I hope I don't get sued for this, but. This is for fun. I'm not making any money off it. I don't even get like ad revenue for these videos. So don't sue me, Epic, please. I'm just trying to have fun. But yeah, like I said, this will make spring more fun than just seeing a bunch of dots or a bunch of cubes kind of like springing this. But I think this will be an awesome way to really play with springs, because this is kind of a fun thing. And like I said, we can then transition to WebVR and then put ourselves inside of it, and then maybe use our controllers to pretend that we're actually controlling those handles on the inside, and we can sit inside, look up and around, and rotate and just drive, and maybe even control the gun and shoot the plunger. So there's some really fun stuff that I'm planning to do in the future. So yeah, I probably wasted so much time in this video talking about the future, but I'm just so excited. I'm like having fun with this. The first year and a half was just really a lot of grinding, and now I'm able to do some fun stuff, and that means you guys get to do some fun stuff, and this is awesome. Like, just the total notion of doing the VR and sitting inside that, and then just driving around in this 3D space and maybe shooting the cannon. I don't know, that's awesome. And it's all web-based. That's like the most exciting part. This is all web-based. This is JavaScript and WebGL, and we're building this crap from scratch. So yeah. I'll see you guys in the next video, hopefully next week. If I have time this weekend, maybe I'll start recording the IK dance, so this way I can go straight into building this with spring physics. Yeah. So yeah, like I said, I got this working. So took the code from one of our videos, fixed up the mesh, had to fix up several of the bones on this mesh. This is actually all bones. This is all armature. And that's another beautiful thing. This is all armature work. So we get to see how the armature for this works. It's kind of neat. So armatures are not just for human bodies. We can use that to control. So I'm actually not rotating the ball. The ball is attached to a bone, because this is actually just two meshes. The sphere and the canopy, or like the chair, that's all one. Just two meshes. So, but they're all controlled. Everything is being controlled by an armature. So there's like maybe 15 bones in total for this system to control. But yeah, all I'm doing is just rotating one bone. So yeah, So that's it. I wasted enough time. I'm just having fun with this. I just can't wait till I can sit inside this thing and just like, yeah, just like this. I just can't wait till I can just do this. I'm actually going to buy a Windows. When I get to that point, I'm going to buy a Windows VR headset because my Vive thing, like one of the stupid sensor boxes. One of them died and took months to get it repaired, and it's a pain in the ass to kind of set up and go. So I'm thinking about, since the Windows VR is cheaper now, it's only like $300. The Samsung Odyssey. I was thinking maybe I'll buy that and use that to prototype the VR aspect of it. So this way I don't have to set up sensors and everything else. I just plug it in and just hopefully just go for it. So it's supposed to work with web stuff. So yeah. I can't wait till we do this in VR. This is gonna be totally awesome. So yeah, I guess I'll see you guys in the next video, and I hope you have fun and you enjoyed moving Vegeta around. So next time we'll have him dance for us, like the monkey that he is, because he is a monkey. He's got a monkey tail. All right, see you guys in the next video. Goodbye.